In this video, I will draw the electric field lines around a dipole. A dipole is this arrangement where you have a positive charge and a negative charge, and that's what a dipole is. So this is a dipole. Ignore this charge. This charge is not part of the dipole. It is my test charge. And we're going to consider what this little test charge does. Come on, move with me. In different scenarios. So first, let's put it really near the other positive charge. It would be repelled by this positive charge and attracted to this negative charge and would accelerate to the right in that direction. And so one field line around this dipole arrangement would go from positive to negative. If, oh no, my test charge changed colors. All right. If this test charge was placed maybe here, we could see it would shoot radially away from that positive charge, but eventually it would be attracted to this negative charge. So the overall arc of its path would look something like that. It would, it'd move around like that. So our field line here would go from positive to negative, and then symmetrically we can see that something down below would look the same. And if we get further away, the same pattern happens, just further and further away from that positive charge. Here the arc gets so big that it'll go off the page and it'll come back around this way. Similarly, it'll go off the page, come back around this way. And then the last line that we need to consider is, what if I put a positive charge at the very left edge here? The positive test charge would be repelled directly to the left. And then what about if I put it over here to the right of the negative charge? It would be pulled directly to the left toward that charge. So we also have a field line that goes to the left away from the positive charge and then incoming to that negative charge. We could think of this line as this one goes left all the way to negative infinity, loops back around to positive infinity, and then comes back in. And this is what the electric field lines around a dipole look like. And again, the spacing of the lines indicates how strong the field is here. So if we grab this zone, they're pretty strong. Compare it to this zone, they're not as strong. So the field gets weaker and then stronger the closer you get. If we wanted to track which direction the electric force on a charge is at any given time in this field, we might just throw it on top of one of those field lines. And then the electric force is going to be tangent to that line. So the electric force is tangent to field line. Similarly, the electric field strength at that point is tangent to the field line. So the electric field vector is tangent to the line as well. And we know that this works out because the electric force and the electric field on a test charge must be in the same direction due to the fact that they're proportional to each other. Remember, this is the gravitational force equals mg of electricity. We're changing out mass with a charge, changing out gravitational field with electric field. All right, so that's our dipole arrangement here. We cannot use the electric force equals Q over r squared directly at any point because there are two charges. However, we can do the vector sum of the individual electric fields to figure out the net electric field. And we'll do some practice with that in class. All right, there we have it, the electric field lines around a dipole arrangement.